Hello everyone. We'll continue our discussion on reaction dynamics in solution, and remember that what we did in the last part is basically we considered the diffusion limited rate constant, and we derived an expression for the diffusion limited rate constant as rewriting it once again. K is 4 pi dA plus dB, where dA and dB are the diffusion coefficients for the reactants A and B, and times R, where R is basically the radius or the sum over the radius of the two reactant species, and this 4 pi capital R square is the volume where actually within which the reaction is occurring. Now today what we are going to discuss is basically the reaction between ionic species, but for the moment we are not considering any particular ion, like it's a positive ion or negative ion or something like that. So it can be between two opposite ions, it can be of same similar ions, but similar ions, you know that they will repel each other, but there can be reactions. I mean, we can make it more general in that sense, that we will just keep everything in terms of our electrostatic potential. So what we are going to do is that we are defining mobility, which has been already introduced to you, and we are writing the mobility. So let me just write it also. This is mobility, or the mobility of the ion. So that mobility we are defining as the velocity of the ion divided by the potential gradient, and in three-dimensional the potential gradient is the gradient of phi, where phi is the potential. So this is the potential gradient, or the gradient of the potential. So what it means actually, since the mobility is a constant, the velocity is actually proportional to the potential gradient, which makes sense because if we have a higher potential gradient, the ions will move faster, or the charged species will move faster. Now if you remember, in deriving this equation, we started from the diffusion equation, where we defined the flux as along some particular direction Jz as negative of the diffusion coefficient times the concentration gradient along Z. But now we will have an extra component to it, and that extra component we are writing it as, I am writing it as plus Z, where Z is the charge of the ion, divided by the modulus of Z. So basically it will dictate the sign of that ion, whether it is a positive ion or negative ion, and then multiplied by the ionic mobility, and times the concentration of the ion, and times the potential gradient del phi del Z. Now I am now using instead of the gradient, the three-dimensional gradient, I am just using a one-dimensional form. So basically mu into del phi del Z, this term, so that is nothing but the velocity. So you can actually see here, so it is nothing but the C, the concentration, times the velocity, and times the charge species direction, like whether it is moving in or moving out. So you can actually take the negative sign within the outside the bracket, and now this describes actually the total flux. The first part is purely diffusive, which does not contain any ionic contribution, and the second part is the purely ionic contribution, how the ions are moving against this potential gradient. So this part is the first part is an stochastic movement, and the second part is basically an active motion of the ions. Now again at equilibrium we can actually assume that the net flux will be 0, and it is basically, you can set it to be 0 at equilibrium. So this is exactly the same approach which we were doing, and then we can rearrange the terms. So you can see that I have to basically integrate the C dependent term, and we could have, instead of writing it as del C del Z, we could have written it as dC dz, because there is no other coordinate. We are just considering it as a one-dimensional problem right now. So it is identical to dC dz. So we can actually rearrange it. So let us follow it. So what we will have is I'm keeping this term on the left hand side and then dividing it by C. So dC by C. So I'll be left on the right hand side as minus Z by modulus of Z, and then mu. The C I have already taken on the other side, and then I'll have divided by the diffusion coefficient because there was a d here associated with dC by dZ, and then I'll have del phi and I'll have del Z. So del phi del Z into I'll have dZ, so that will overall make it d phi. Again, this potential also, as I have written it as a variation of partial derivative, it is nothing but d phi dz. Now we'll integrate this equation, and the integration is again pretty straightforward in this case. So z is a constant, mu is the mobility, that is also constant, and but before doing this integration, we'll just make some approximation. So let us not integrate it in this way. So let us see actually how, let us discuss first how the integration should look like. Now as you can see, it is dc by c, so the integration will be some logarithmic integration, ln c, and then we can also put some initial condition that at phi equal to 0 the concentration is C0. So before attempting the solution, let us assume that this solution, what we are guessing, that it will have some logarithmic solution, something like say ln c, and if I put the initial condition that C0 was the concentration at phi 0, and then on my right hand side, if I just remove the logarithm, it will be C is equal to C0 into e to the power something. And let us assume that it has an dependence, this concentration has a dependence which is something like a Boltzmann type, in the sense that C is something like C0 into e to the power minus some potential energy U, which we do not know at this moment, divided by kBT. Now what is U? Now U is the electrostatic potential, and by definition U is nothing but if the it's a potential energy, it is nothing but Z times E is the fundamental charge, and into the phi, where phi is basically the electrostatic potential. So the potential energy is nothing but as you know that it's basically the how to get the energy. So if we bring the unit positive charge, that is basically defined as the potential, right? The forces which is felt in bringing the unit positive charge. So we have to just multiply the charge with itself, and then we will get the total potential energy. And then what we can do is that we can substitute this value into this equation, and if we do that, you will get that mu by d is nothing but you can get an estimate of the diffusion connection of the diffusion coefficient with the mobility, because remember that one part is coming from the mobility or the electrostatic, the other part is coming from the diffusion coefficient, and what we did is basically kept a ratio of between them. Now you can show it very easily. So the way you show it is that you write C is C0 e to the power minus ZE phi by kBT, and then basically you can take the derivative ln C by C0, and then just equate it. So what you will get is dC by C, and then you just equate left hand with right hand, then you can easily figure out this equation. And then the total flux now becomes in terms of this whatever we have written here. So you can rewrite this equation as, so let us follow the first equation, which was Zz, the Z component of the flux is nothing but minus d into del C del Z. I can write it as right now dC dz, plus I had Z by Z magnitude of Z, and times mu C into d phi dz. Now I have already given a value of mu by d. So using that, you can easily show it that it will be C by kBt, and times will have du dz, where we have taken the diffusion coefficient common. So this is the modified equation for the reactive for the flux, of course, which is equivalent to the reactive flux that we are going to connect eventually. So we can now say by analogy that actually this is the jet component of the flux, but in reality the total vectorial flux will be something like minus d into, instead of a d dz, it will be just the three-dimensional gradient of the concentration, plus we'll have C by kBt and the gradient of the potential. And so this is a general equation for the flux, including the effect of ionic mobility in 3D. So flux for 3D, or we can actually write it flux including mobility of ions, which is in presence of a potential, of an electrostatic potential, in presence of an electrostatic potential, which was phi, but we in this equation we have connected the phi with the potential energy, which is U, in 3D. This is basically the 3D distribution. Now we can actually solve this equation. We have the flux equation, and what we do, if we go back and think about how we derived it, what we did is basically starting from this equation that the rate of product formation is nothing but equal to the reactive rate, if you follow this equation, times the bulk concentration of A times the local concentration of B at the reaction zone, and then it is multiplied by the J reaction. Right now J reaction is equivalent to the J itself, into 4 pi r square into A bulk, and then all we are going to do is, instead of writing this J as something like dA plus dB into this, we are going to actually include the electrostatic potentials effect, and that's what we are going to do. So on my left hand side I will have the rate as Kr. I'm using the similar notation as we used in the last lecture. A equilibrium, I think I was using instead of a equilibrium notation, I was using the bulk notation, because this is the bulk concentration of A, and times the concentration of B at a position R, which is the position where the reaction is occurring, and which is equal to A bulk times I will have 4 pi r square times I will have dA plus dB, and then I will have so this D, remember this is a generalized D for one species. For two species we know that there will be a net flux because A is moving towards B and B is moving towards A. So instead of D, all the D's will be replaced by dA plus dB, and the flux we are writing it as if you remember that JAB, we are writing it as minus of JA plus JB. That way we are writing it. These are all vector quantities. And secondly, we have also used the fact that this J reaction is identical to the JAB, and it is also diffusion limited. So I'll have two terms. The first term is the time derivative of the spatial derivative of B, and which is the concentration of B, how it varies with the radius. Radius means the distance from the central ion, which is A, and plus I'll have the B divided by kBt, and times I have a potential which is du dz. So this is the overall expression for this, because remember that C is basically the concentration. Instead of C, I am just writing B in third bracket, that represents the concentration of B. Now again, ideally instead of du dz, I should use du dr, and again I am not using the gradient sign here. The reason being, actually it's a gradient, but ultimately the gradient depends on only the radial coordinate, not on the angular coordinates. Now all we are left with is basically to rearrange and integrate this equation. So what we see here right now is that we have a equation for Br, and remember that this is basically a constant, a concentration of B at the reaction zone, and then this is also constant, A bulk. Anyway, A bulk will be eliminated from both sides eventually, and also I have a B, and this B is nothing but the it's a variable. It's basically how the concentration is varying with the radial position as we increase the distance from the central ion, which is the D. Now we can actually rewrite the right hand side as this. So A bulk times 4 pi r square dA plus dB, and then look at it carefully. I'm just writing it as e to the power minus ur by kBt, and then ddr of B, and again B is a function of r, times e to the power ur by kBt. Now you note here what we have done, you can easily check it. So if I take this derivative, if I do it, so what I'll get the first derivative as dB dr, and times I'll have the second term e to the power u by kBt, plus I'll keep the first function constant B, and then derivative of the second function, which is basically 1 over kBt. So this kBt comes here into du, or let me just first do the exponentials derivative. So it will be e to the power minus e to the power plus u by kBt times du dr. So now we are multiplying it by e to the power minus kBt. If I just multiply it by e to the power minus u by kBt, you can see that this and this cancels, and also this term also gets cancelled. So we are actually getting back our original equation. So this is basically a very clever way of writing the above equation. So ultimately what we are getting is, now we are going to actually rewrite this equation, the entire equation, because as you can see here is that I have a derivative of this entire quantity B times e to the power ur by kBt, something like that. So what I'm going to do is basically divide both sides by, so dividing both sides by, one is this thing, the A bulk, because that will get cancelled, A bulk, times, suppose I want to do the r square r integration on my left, so I'll also divide both sides by r square, and also I want to basically eliminate this term, so into e to the power minus u by kBt, and again u is a function of small r. And since I'm doing the r integration on my left, so we have to multiplying it by dr. So then what we will get is a very interesting expression is k r. This small r is a reactive rate, remember. So a bulk will cancel. So I'm getting from here. So I'll have b at r, and then I'll have I'm divided by e to the power minus u by kBt. So I'll have e to the power plus u, which is a function of r, by kBt, divided by I will have r square because I divided both sides by r square, and also multiplied by dr, and then I'll have this line. So follow carefully. So I'll have this thing is already got cancelled, and then the r square will also be removed, and this part I have already won't be there. So what I'll have is 4 pi, I'll have dA by dB, dA plus dB, and then I'll have d. Now this entire expression, let us have a look at it. This integration, actually you can keep it for the time being like this, e to the power u by kBt. This is total derivative. Now we can actually straightforward way integrate it, but the problem here is that if I just want to integrate it, remember that kr is a constant, br is also a constant. If I integrate it like this, now the left hand side integration I cannot do immediately because I need to know what is the form of u of r, because I do not know yet how the potential varies with the distance. So since I do not know this form, I can simply say that I'm just keeping it as constant. And again the limits I am setting when r is equal to r. I know that b is nothing but equal to br, and we'll see it actually. So let us not write the limit right now, because we'll be evaluating it at small r equal to r, and small r is equal to infinity, and we'll see what we'll get the right hand side. So this integration, I'm defining it to be a new quantity. Suppose I call it this integration, integral capital R to infinity, e to the power u r by kBt divided by r square dr. So remember that it depends on the nature of the potential and the potential energy we just wrote, but we do not know explicit form of u, how it varies with small r. So that's why you cannot evaluate it, and I'm just writing it as 1 over beta. So we'll just keep it as 1 over beta. So if we use that, then this equation becomes, let me just rewrite it. So I'll just write it as kr b at position r divided by beta. So that is equal to 4 pi dA plus dB, and then I have to evaluate this integral, but this is just a straightforward integral, but I'm writing it as b into e to the power u by kBt evaluated at r is equal to, small r is equal to r, and small r is equal to infinity. Now that we can easily figure out dA plus dB, and then it is very easy to figure out. Now you see here that when the upper limit you first look at, when r is equal to infinity, we know that b is nothing but equal to the bulk concentration, and the lower limit and again the u infinity, also u at r equal to infinity, that also we are taking to be 0, because it is basically the potential energy at infinite distance. So when there is no influence of the first charge A, and then also at when r is equal to capital R, so we know that this is nothing but b at r, and I'll have e to the power u at r divided by kBt. So that way actually we can write it, and then we can actually rearrange the terms. So we are done with the integration. So let us just rearrange it. So we'll have BR, B at in position R, times I'll have KR divided by beta. So I am basically taking this BR common, just like we did in the last part also, but last time, but we did not have this equation that time, because that is the potential that depends on this electrostatic potential. Also we did not have the beta that time. We'll come to it. And then what we have inside is I'll have a plus sign, because I'm bringing this term on the right hand side to left hand side. So I'll have e to the power u at r divided by kBt. So this is not a variable, this is basically a constant, u at r, and multiplied by, I have 4 pi dA plus dB, that is always there, and that is equal to 4 pi dA plus dB times I have the d bulk. So now we can easily see what will be the value of B at R. So that will be nothing but B at bulk and times the 4 pi dA plus dB, but we can actually divide the numerator and denominator again by 4 pi dA plus dB, and you know that how to do it. And then I'll have two terms, basically. One will be I'm just writing the second term in the denominator, e to the power u of r divided by kBt, plus I'll have kr divided by 4 pi dA plus dB into beta. So remember that all we have to evaluate is the rate. So basically what we can say that u of r, or meaning actually the potential at the reactive zone, it's basically will be very small. Why? The reason is actually you can think about it, at infinite it is 0. Now when if we assume that the two ions are in contact, then actually when they are far apart, then there is a potential acting on them. So there is a huge potential energy between them, but when they are in contact, they are kind of in an equilibrium position. So then actually that value will be very small, and usually we can actually ignore that value, in the sense that we have an exponential of e to the power we have e to the power ur by kBt, and since that value is very small, we can actually approximate it, the exponential, to be truncated in the first term only. So we are just using it as 1 itself. Now don't get confused that when I am keeping the r equal to infinity, the u of r was basically 0. Now as I am bringing it together closer to the second ion, the potential is increasing in the negative sense. But when the ions are in contact, then I can assume that potential has gone into its minimum position. So that's why you are ignoring it, and we are saying that compared to kBt it is small. So that's the entire thing. So then I can actually approximate ur since it is very small, and then we can just remove this thing, and you can just write it instead of this entire term, we can actually write it as 1. And then as we know that the rate of product formation, the dP dt, so this is following the same kind of notation we have been using, dP dt, that under this approximation becomes so the B bulk is nothing but if we go back, what was the dP dt formula? So it was this, it is basically Kr times A bulk into Br. So let us just write it, it is Kr. So up to this point, this is the exact thing. So this is K under diffusion limited rate. So we are going to approximate it again. So Kr into A bulk times B at a position R. So B at a position R, that's what we have evaluated. So I'll have Kr times A bulk, or A bulk we can actually write it later. So we'll have 1 over, so this term I have taken to be 1, I'll have Kr by 4 pi dA plus dB into beta and times A bulk into B bulk. So these are the bulk concentration, and this was an approximation because here we have made the e to the power term to be 1. And then again we can approximate that this reactive rate, or the rate of the second step where actually the products are being formed. So every contact or every encounter is giving me reaction, then that will be much higher than this diffusion limited term dA plus dB, which also contains the term which is beta. And remember that beta is coming from this integration that I have e to the power u by kBt divided by r square dr, that integration where r is going from the contact distance to infinite distance. And if I approximate that, then you know how to do it. What we get from here is I'll have, I'm just expanding it, it is Kr, then I'll have 4 pi dA plus dB into beta plus Kr and divided by 4 pi dA plus dB. So that I am moving into the numerator, dA plus dB, and then I have A bulk into B bulk, and then what I can say is that this term, using this condition, so we can now write including beta. So you can now write that this term is much smaller than this Kr term, so you can ignore it, and the moment you ignore it, this Kr gets cancelled with this Kr, and then we get the final expression as the rate of product formation is basically 4 pi, there will be a beta here, dA plus dB into beta times A bulk into B bulk. So what we see here, the effective rate constant as before is nothing but 4 pi dA plus dB, but there is an additional term which is the beta, and that's how it is basically getting included. And that's a beautiful way of showing it, that although this beta has a very complicated expression because we did not included it, and we just said that it is basically the variation of the potential, and how it depends on this integration on the variation of the potential. We just noted term which is beta, and the only difference we see from the diffusion under the diffusion limit between the species which are non-ionic or non-charged and the species which are charged is this small difference, which is the beta. And interestingly, so earlier as you can see that the earlier expression contained an r, it was 4 pi dA plus dB into r. Now if you look at it, so the dimension wise it should be the dimension of capital R. So let me just rewrite the two equations. So for under the diffusion limit, so under the diffusion limit, which means the limiting step is the diffusion of the encounter itself, because once the encounter, every encounter is giving me the reaction, which means that Kr is large compared to the other terms, And then for non-charged species or non-ionic species versus the ionic species, the effective rate, in one case we are getting 4 pi dA plus dB, which is the addition of the diffusion coefficient of the two species times R, and in the other case we are getting K effective is 4 pi dA plus dB times beta. Now as you know that R is basically the contact distance, and where this beta is nothing but the integral e to the power u by kBt divided by r squared dr. Now if you look at it carefully, it is basically e to the power u by kBt is a number, and then dr by r square. So e to the power u by kBt is basically unitless, and dr by r square has a dimension of basically the same dimension, the contact the r dimension. So dimension wise they are still the same, and remember that we wrote it as a 1 over beta, not beta. So I should also write it here. So that was beta inverse, it is 1 over beta. And then beta has a dimension of 1 over r, 1 over length. So beta inverse has a dimension of 1 over beta has a dimension of 1 over length. So beta has a dimension of length. So thus we see the only difference coming between these two equations is here, and where in one case we have included the electrostatic potential, and the other case it is just simply the distance of the contact pairs, center to center distance. So thus we have shown that how one can actually mathematically develop the effective rate constant under the diffusion limit for ionic and non-ionic species. So we'll just conclude our discussion on the reaction dynamics in solution here, and then we'll basically summarize the entire portion that we have covered. Thank you.